Educational GMAT. Your partner in your GMAT journey.
All right, let's start the class. This is supposed to be a very basic and fundamental class where we'll be discussing these basic factors and multiples concepts. These would primarily be a refresher to those who have completely lost touch with their class 6th, 7th, 8th concepts in quant. But these concepts are extremely important since we will build upon them in our GMAT specific quant classes. Let's start with the definition of a factor. A factor is a number, or rather a factor of a number divides that number exactly. A factor of a number divides that number exactly. For example, can you guys try doing this? Find the list of factors of 12. What are the factors of 12? So what are we looking for here? A number that divides 12 exactly. A number that divides 12 exactly. What do I mean divide 12 exactly? Basically, there will be no remainder, right? For example, 2 clearly divides 12 exactly, right? So 2 clearly divides 12 exactly. Why? Because when you divide 12 by 2, then you get 6 and remainder is equal to 0. Since this is the case, 2 will be called what? A factor of 12. So the way 2 is a factor of 12, this question is asking you to find out the entire factor list of 12. That factor list obviously would include 2. What are the other numbers that this factor list would include? So one way is to find the products of numbers that give us 12, right? So for example, 12 is obviously 1 into 12. 12 is also equal to 2 into 6. 12 is also equal to 3 into 4, right? So these are the products, right? So products of numbers. So product of 1 and 12 gives 12. Product of 2 and 6 gives 12. Product of 3 and 4 again gives 12. So what is the list of factors of 12? What is the list of factors? All of these. 1, 2, 3, 4, 6, and finally 12. So we have now arrived at the list of factors of 12. 1, 2, 3, 4, 6, and 12. And if you notice, for each of these, right, for each of these numbers divides 12 exactly with remainder as 0. You do remember that every number has 1 and the number itself as its factors. For example, 12 had 1 and the number itself as factors. So any number would always have 1 and the number itself as its factors. For example, 14, I'm just taking a number randomly. Among the other factors, it would always have 1 and the number itself as its factors. And I'm hoping by now you to realize that the other factors of 14 would be 2 and 7, right? But then these numbers could vary from one number to another, but then the number 1 and the number itself would always be the factors of any number. No factor of a number can be more than the number itself. If you think about it logically, this makes sense. For example, here we were looking to find out a list of factors of 12, So the entire list of factors of 12 would not include a number greater than 12. Similarly, if we are looking for factors of 14, all the factors of 14 would be lesser than or equal to 14, right? So anything, you can take any number. For example, what are the factors of 56? All the factors of 56 would be numbers that are lesser than or equal to 56. This is what this point states. No factor, no factor of a number can be more than the number itself. In other words, all the factors of a number would be lesser than or equal to the number itself. So we covered factor on the last slide. We cover multiples on this slide. A multiple of a number is the product obtained when a given number is multiplied by the same or any other number. So let's start with this quick exercise. Find the multiples of 12. Find the multiples of 12. What are the multiples of 12? Well, this is how you find out the multiples of 12. 12 into 0, which is 12, 12 into 1, which is 12, 12 into 0, which is 0, 12 into 1, which is 12, 12 into 2 is 24, 36, 48, 50, and so on. So products obtained by multiplying 12 with various numbers, multiplying 12 with various numbers gives you multiples of 12. So products obtained by multiplying 12 with various numbers, by multiplying 12 with various numbers, that's how you get the entire multiple list of a number. In this case, we were interested in finding out the multiple list of 12. Every number is a multiple of itself, right? Again, take any number. For example, if we have to find out the multiples of 56, well, 56 would be a multiple of 56 for the simple reason that any number when multiplied by 1 gives itself. Every number is a multiple of 1. Every number is a multiple of 1. Why do we say that? Let's find out multiples of 1, right? The way we found out multiples of 12 here, let's find out the multiples of 1. Again, how do we do that? 1 into 0 is equal to 0. 1 into 1 is equal to 1. 1 into 2 is equal to 2. 1 into 3, 3. 1 into 4, 4, and so on. So notice 0 is a multiple of 1, 1 is a multiple of 1, 2 is a multiple of 1, 3, 4, 5, 6, and so on till infinity. So every number is a multiple of 1. Every number, by every number I mean every integer, is a multiple of 1. All right. Proceeding further, every multiple of a given number is equal to or greater than the number itself. Well, this obviously has an exception, and this is the exception. When you multiply by 0, so the answer is 0. So 0 is a multiple of every integer, but apart from 0, every multiple of a given number is equal to or greater than the number itself. For example, let's take 6. Let's say we have to find out the entire multiple list of 6. How do we find out? As I said, apart from 0, how do we find out the entire multiple list of 1? 6 into 1, 6 into 2, 6 into 3, 6 into 4, and so on. So 6, 12, 18, 24, and so on. This comprises and so on, by the way, till infinity. So this comprises the entire multiple list of the number 6. And if you look at it, every multiple of 6 in this case is equal to or greater than the number 6 itself. By this, I'm hoping you are able to observe the contrast with fractions that we discussed on the last slide. What did we discuss with respect to the fractions? That that every factor of a number is either equal to or lesser than the number itself. In fact, it's a good point to reiterate. Every factor of a number is equal to or lesser than the number itself. For example, what we did on the last slide was factors of 14. What are the factors? 1, 2, 7, and 14. So every factor of a number is either equal to the number or lesser than the number itself. And what are we discussing here? What we are discussing here is that every multiple of a given number is equal to or greater than the number itself. Lesser than was for factor, greater than was for multiple. For example, in fact, let's continue with the same theme. What are the multiples of 14? Again, as I said, if we leave 0 as an exception, multiples of 14 would be 14 into 1, 14 into 2, 14 into 3, and so on till infinity. So now notice every multiple of a given number is either, notice this is 14, 28, 42, and so on. So is equal to the number, or greater than the number itself. Every number has infinite number of multiples. This I think should be very evident. For example, if we find out the multiples of 14, what would those multiples be? 14 into 1, 14 into 2, 14 into 3, 14 into 4, 14 into 5, and so on till when? Infinity. So every number has an infinite number of multiples. 0 is a multiple of every number. Why is 0 a multiple of every integer or number? Because any integer, when multiplied by 0, gives 0 as an answer. So 0 is a multiple of every integer. Okay, let's do this quick quiz. Is 7 a multiple of 49? What do you think? Is 7 a multiple of 49? Of course not. 7 is not a multiple of 49. 7 is actually a factor of 49. Is 9 a multiple of 3? Absolutely. 9 is a multiple of 3. How do we know that? 3 into 0 is equal to 0. 3 into 1 is equal to 3. 3 into 2 is equal to 6. 3 into 3 is equal to 9. So notice, so this basically is, and so on till infinity. This is the entire multiple list of the number 3, and 9 appears in that list of multiples. So 9 is definitely a multiple of 3. Is 18 a factor of 54? What was the definition of factor, by the way? What was the definition of factor? That we'll go back. Actually, let's go back. Notice a factor is of a number divides that number exactly. Again, what do I mean divides that number exactly? that remainder is equal to 0, right? So now from that perspective, is 18 a factor of 54? The answer is yes, because 18 divides 54 exactly, because the quotient is 3 and the remainder is 0. Which integer is the smallest factor of every integer? We did discuss this on the earlier slide. Which integer is the smallest factor of every integer? Remember, 1 is a smallest factor of every integer. Again, let's take 12 into consideration. What are the factors of 12? 1, 2, 3, 6, 4, 6, and 12. Similarly, what are the factors of, for example, 14? That would be 1, 2, 7, and 14, right? So 1 inevitably would always be a factor of every integer and is also the smallest factor that any integer can have. Which integer is the greatest factor of every integer? We discuss a couple of things. One is, what are those two things? One is that a number is always a factor of itself. And what was the second thing that we also discussed? That what was the other thing that we discussed? That the factor of a number can never be greater than the number itself, right? Again, for example, if we look at factor list of 12, so that would be 1, 2, 3, 4, 6, and 12. So a number is always a factor of itself. And secondly, the factor list of a number can never comprise a factor that is greater than the number itself, which means all the factors of 12 have to be lesser than or equal to 12 itself. So if you combine these two things, we get an answer to this question. What integer or which integer is the greatest factor of every integer? The number itself will be the greatest factor of every integer. What is the largest multiple of any integer? So again, let's consider 12. What's the entire list of multiples of the number 12? 12 into 0 is 12, 12 into 1 is 12 into 0 is 0, 12 into 1 is 12, 12 into 2 is 24, 12 into 3 is 36, and so on till when? Infinity. And as we discussed on a previous slide, every integer would have an infinite list of multiples. So largest multiple of any integer would be infinity. What two integers are multiples of every integer? What two integers are multiples of every integer? Again, we've already taken 12 as an example. We can now take, for example, 14 as an example. What is the entire list of multiples of 14? 14 into 0 is 0, 14 into 1 is 14, 14 into 2 is 28, 14 into 3 is 42, and so on till infinity. Right? So what two integers are multiples of every integer? Well, 0 is a multiple of every integer, and the number itself is always a multiple of every integer. So 0 and the multiple itself. What integers are factors of every integer? Incidentally, the answer is the same. Again, let's take the same two examples. Factors of 12, as we've seen multiple times, would be 1, 2, 3, 4, 6, and 12. Factors of 14, for example, would be 1, 2, 7, and 14. So what two integers are factors of every integer? The number 1 is a factor of every integer, and finally the number itself, right? 14 is a factor of 14, 12 is a factor of 12. So the integer 1 and the number itself would be factors of every integer. Let's now come to the very important concept of LCM, which is the least common multiple. Having done multiples and understood what a multiple stands for, this is an appropriate time for us to introduce to you the concept of least common multiples. So let's find out the least common multiples of 8, least common multiple of 8, 12, and 16. So before we do that, let's first find out the multiples of 8. So again, as I said, barring 0 as an example, what would be the multiples of 8? 8 ones are 8, 8 twos are 16, 8 threes are 24, and so on. What would be the multiples of 12? 12 into 1, which is 12, 24, 36, and so on. And what are the multiples of 16? 16 ones are 16, 16 to the 32, 16 to the 48, and so on. So these are the multiples of 8, 12, and 16 respectively. The question, however, is asking us, what is the least common multiple? What does it mean, common multiple of 8, 12, and 16? A multiple that is, or rather a number that is a multiple of 8 and is also a multiple of 12 and is also a multiple of 16. So if we look at these three lists of multiples, what is the least common multiple? In other words, what is the least number that is a multiple of 8 and is also a multiple of 12 and is also a multiple of 16? 48. So what's the LCM of 8, 12, and 16? The answer is 48. And this is the log division method, which is generally uh, a much more handy and concise way to find out the actual LCM, the least common multiple. So since we had to find out the LCM of 8, 12, and 16, what we do is find out a prime number that is a factor of all these three numbers. So 2 is a prime number that's a factor for all of these three. So you put 2 here, 2 fours are 8, 2 6 are 12, 2 8 are 16. Notice 2 continues to be a prime factor for all these three. So again, we put 2 over here, 2 2s are 4, 2 3s are 6, 2 4s are 8. Now notice 2 continues to be a common prime factor for these two. So you again put 2 here, 2 ones are 2. This 3 obviously is not a multiple of 2, so we let it remain there, and finally 2 to the 4. Now notice there is no other common prime factor for these. So then how do we find out LCM, the least common multiple? 2 into 2 into 2 into 1 into 3 into 2, which again, so it gives us the answer as 48, which was the answer that we arrived here as well from a more conceptual perspective. So this is how you find out LCM. Incidentally, any idea what? So mind you, this is the lowest or the least common multiple of 8, 12, and 16. What would be the other common multiples of 8, 12, and 16? Think about it. What would be other common multiples? 48 is obviously a common multiple. What are the other common multiples? Well, other common multiples of 8, 12, and 16 incidentally would be 48 obviously is the least common multiple. The next common multiple would be 48 into 2. The next one would be 48 into 3, 48 into 4, and so on till infinity. In other words, as far as the common multiples of 8, 12, and 16 go, basically this is they will repeat with a cyclicity of 48, right? Cyclicity of 48. 48, 48 into 2, 48 into 3, 48 into 4. So this cycle will keep getting repeated. Okay, this is another method to find out the LCM, which is through the factorization method. Let's first do prime factorization of 8, 12, and 16. So 8 so this is how you do prime factorization, by the way. You put 8 over here. 2 is a prime factor, so 2 4s are 8. Now 2 is continues to be a prime factor, so 2 2s are 4. Now 2 again is a prime factor, so 2 1s are 2. So 8 is nothing but 2 into 2 into 2 into 1. How about 12? 2 is a prime factor, so 2 6 are 12. 2 continues to be a prime factor, 2 3 is 6, and 3 1s are 3. And we apply the same approach to 16 as well. So basically 8 is 2 cube, 12 is 2 square into 3, and finally 16 is 2 raised to the power of 4. Now, how do we find out LCM of 8, 12, and 16 given this prime factor list? How do we find out LCM? This is how you find out the LCM. Keep looking for highest powers of the various prime factors of 8, 12, and 16. So let's now apply this approach. LCM of 8, 12, and 16. What do we look for? Highest powers. Now, if we look at 2 here, right? 2 is a prime factor of 8. Now, what is the highest power of 2? 2 cube. In this case, what is the highest power of 2? 2 square. In this case, what is the highest power of 2? 2 raised to the power of 4. Right? So 2 has the highest power of 4 across these three integers. So 2 raised to the power of 4 would figure here. Next, we come to the other prime factors. 3. Notice there is no power of 3, right? Basically, it's 3 to the power 0 here, is 3 to the power 1 here, and again 3 to the power 0 here. So what is the highest power of the prime factor 3 across the three numbers? Well, 3 raised to the power of 1. So 3 is the power of 1. And if you calculate this, how much is it? 16 into 3, which is 48. Right? So if you remember, this was exactly the same answer that we were getting through the long division method as well. So 48 is the LCM of 8, 12, and 16. All right. Three integers A, B, C can be expressed as this. A is equal to m square into n cube, C is equal to mn square p, and d is equal to mn square p raised to the power 4, where m, n, and p are all prime numbers. So what is the LCM of A, B, and C? This question is a direct application of the concept that we discussed here. And the specific rule that we have to remember is that LCM is nothing but a product of highest powers of the various prime factors. So m, n, and p are already prime numbers. So what would be the LCM of A, B, and C? So let's first start with the prime number m and look for its highest powers across the three numbers. So m square, m, and m. So the highest power is obviously m square. So we put m square over here. Now let's come to n cube, n square, and n is again n square. So again, what's the highest power for prime factor n? N cube. So you write n cube here, and finally we come to p. There is no presence of p here. There is a p here, and there is a p raised to the power of 4. So what's the highest power of p across the three integers? P raised to the power of 4. So into p raised to the power of 4, that would be the LCM of A, B, and C. Direct application of the formula that we discussed on the last slide. M square into n cube into p raised to the power of 4. All right. Let's do this question as well. I'll give you guys a couple of minutes to think about it. Not difficult at all. Okay. It is given to us that the LCM of these two integers is this. So we have to find out the value of p, the value of p. How do we do that? How do we do that? Let's again express, each of these as prime factors, right? So 12 x cube y square, and then what do we have? 18 x raised to the power of p y cube. So 12 is obviously 2 square into 3. And then we have obviously x cube and y square. How about 18? 18 is 2 into 3 square into x raised to the power of p into y cube. So now if we look at LCM of these two integers, again going by what we discussed, what would the LCM be? Essentially LCM would be the product of the highest powers, right? Product of the highest powers of each prime number, correct? So now LCM would be notice, so we start with 2. This has 2 square. This is just 2. So the highest power of 2 is how much? 2 square. So we put 2 square here. Next we come on to 3. Now this has only 3, which is 3 raised to the power of 1, while this has 3 square. So the highest power of 3 is obviously 3 square. So you put 3 square over here. Next we come on to x. Now x is x cube here, and this is x raised to the power of p here. So we don't know the value of p. So what will be the value of x then in the LCM? X will be basically the maximum value between 3 and p. And finally, when it comes to y square here and y cube here. So y cube is obviously greater. So we put y cube. Now that's the LCM. We are already given that the LCM is 36 x raised to the power of 4, y raised to the power of 3. Now notice this 2 square into 3 square is how much? 36 into x raised to the power of the greater value between 3 and p into y cube is equal to 36 x raised to the power of 4, y raised to the power of 3. Now notice 36 gets cancelled, y cube gets cancelled. So x essentially and the greater value between 3 and p is x raised to the power of 4. So this clearly tells you that between 3 and p, the greater value is 4, which clearly means that p is equal to 4. That's the answer, right? Because had p been lesser than or equal to 3, then we would have had x cube here. The very fact that we have x is the power of 4 means that the value of p has to be 4. All right, find the smallest number which leaves 5 as a remainder when divided by 95 or 114. Think about it. What's the question asking for? Smallest number which leaves 5 as a remainder when divided by 95 or 114. So what we have to do here is, let's do prime factorization. So that would help, rather long division method, to find out the LCM of 95 and 114. So that would be 570. Now let's understand what 570 represents. What 570 represents. 570 is the lowest common multiple or the least common multiple of 95 and 114, which means 570 is a multiple of 95. 570 is also a multiple of 114, right? The question is, what is the smallest multiple which leaves 5 as a remainder? What is the smallest number which leaves 5 as a remainder when divided by 95 or 114? Now think about it. 570 is a multiple of 95. 570 is a multiple of 114. What does it mean? It's a multiple that 570 when divided by 95 gives remainder of 0. 570 when divided by 114 again leaves a remainder of 0. Now here we have to find out the smallest number, right? 570 is a number that leaves a remainder of 0 when divided by 95 or 114. The deviation that we have in this question is, what smallest number leaves a remainder of 5 when divided by 95 or 114? Again, reiterating, this number 570 leaves a remainder of 0 when divided by 95 or 114. So what number will leave a remainder of 5 when divided by 95 or 114? Since we are interested in 5 as a remainder, so then it would be 570 plus 5, which is 575. And because 570 leaves a remainder of 0 when divided by 95, so when we add 5, notice essentially it's this, right? 570 when divided by 95 leaves 0 as a remainder. So if you add 5, then 575 is the number that leaves 5 as a remainder. Same case with 114. 570 leaves, so basically it's 570 upon 114. This would leave 0 as the remainder. And when we add 5 to it, 5 would be the remainder when you divide by 114. So 575 is the final answer. Having done LCF, now we come to HCF, which is the highest common factor. So we're actually considering the same three numbers, 8, 12, and 16. Let's now find out the highest common factor. If you remember a couple of slides back, we discussed multiple ways in which you could find the LCM of 8, 12, and 16. And the LCM that we found out was 48, right? LCM. Now we want to find out the HCF, highest common factor. How do we do that? First of all, we find out all the factors of each of these numbers. So again, we had a discussion about factors. So factors of 8 are 1, 2, 4, and 8. Factors of 12, 1, 2, 3, 4, 6, and 12. And factors of 16 are 1, 2, 4, 8, and 16. So what is the highest common factor? Notice these are the factors of 8, these are factors of 12, these are the factors of 16. So what are the common factors, by the way? What are the common factors of 8, 12, and 16? What are the common factors? One is obviously a common factor, right? What else is a common factor? Notice 2 is a common factor. Common factor means a factor that is basically a number that is a factor of 8, that is a factor of 12, and is a factor of 16 as well. Anything else? Yeah, notice 4 is also a common factor. And we have no other common factors. So these are the sorry, I mistyped it. We are looking at common factors. So these are the common factors of 8, 12, and 16. Now, out of these common factors, which common factor is the highest? That's called the highest common factor. And in this case, hopefully it's very evident that the highest common factor of 8, 12, and 16 is 4. That's the answer. 4. And this is the most common method to find out HCF, which is the factorization method. So how do we do that? First of all, we do prime factorization, which by now hopefully you are very comfortable with. So 8 is 2 cube, 12 is 2 square into 3, and 16 is 2 raised to the power of 4. So what we now find out is, since we have to find out HCF, keep looking for lowest powers of the various prime factors that are common to all numbers for 8, 12, and 16. Now let's do that. Highest common factor of 8, 12, and 16 is what we have to find out. Now notice there is a 2 here, there is a 2 here, and there is a 2 here. So clearly 2 as a factor of 2 all the 3 numbers. What we look for is the lowest power of 2. Notice this is 2 cube, this is 2 raised to the power of 4, and this is 2 raised to the power of 4. So what is the lowest power of 2 that is common to all the 3 numbers? The lowest power is 2 square. Okay, now is there any other number that we need to consider? Notice there is here, but 3 as a factor is not common to all the numbers because 3 as a factor does not exist in this list or does not exist in this list. In other words, the HCF of 8, 12, and 16 remains what? 2 square, which is 4. And by the way, this was the answer that we got here as well. So HCF of 8, 12, and 16 is 4. LCM of various numbers cannot be smaller than the largest of those numbers. LCM of various numbers cannot be smaller than the largest of those numbers. For example, LCM of 8, 12, and 16 cannot be smaller than the largest of those numbers. If you remember a couple of slides back, we found out that the LCM of 8, 12, and 16 turned out to be 48. Similarly, you can do any which number, for example, LCM of 4, 8, and 16. By the way, if you find out the LCM, that would turn out to be 16. So LCM of various numbers cannot be smaller than the largest of those numbers. It's the highest common factor of various numbers cannot be larger than the smallest of those numbers. So again, HCF of, for example, 8, 12, and 16, the HCF of the numbers cannot be larger than the smallest of those numbers. If you remember, HCF of 8, 12, and 16, as we found out in the last slide, was 4. Right? So it cannot be greater than the smallest of those numbers. All right. Yeah, we've taken 9 and 12 as an example. HCF is 3 and LCM is 36. So LCM of various numbers cannot be smaller than the largest of those numbers. Similarly, HCF of various numbers cannot be larger than the smallest of those numbers. All right, this is quite a tricky question, and I'll give you guys 2 minutes for this. Quite an involved question, and then let's discuss. By the way, this is the last question that we do today. Yes. So how do we do that? How do we do this? So find a pair of two-digit numbers. So we have to find out those two-digit numbers whose HCF, highest common factor, is 6 and least common multiple is 168. So what we do is, let's first factorize 6 and 168, basically prime factorization. So this is how we do prime factorization. So 6 is essentially what? 6 is 2 into 3, and 168 is how much? Basically, 2 cube into 3 into 7. So this is how we've done prime factorization. Now, this is where I want you to do some critical thinking. What we have to find out is those two-digit numbers whose HCF, highest common factor, is 6. Highest common factor. What does it mean, common factor? That number should be a factor of both those two-digit numbers, right? So let's take those two-digit numbers. Let's say D1 and D2 are those two-digit numbers. Now, first thing I want you to understand and appreciate is that since 6 is a factor of both D1 and D2, right? So there has to be a 2 into 3 and a 2 into 3 here as well, right? Because only in this scenario would 6 emerge as a factor of D1, and it would also emerge as a factor of D2, right? So we have a 6 here, we have a 6 here. Now LCM is 168 and LCM is this. LCM is this. How do you find out LCM? We did discuss on one of our previous slides that once we find out the entire factor list, then how do you find out LCM? I'll just go back. This is worth a revision. Going back, back. Notice, to find out LCM, what we do is we keep looking for highest powers of various prime factors of the numbers involved. In this case, the numbers involved were 8, 12, and 16. So we keep looking for highest powers. In this case, for example, if we look at the prime factorization list for each of the three numbers, the highest power of 2 was 3. So the highest power of 2 was 3. here. The highest power of 2 is 2 here. The highest power of 2 is 4 here. So we write 2 raised to the power of 4 in LCM. And then as far as 3 goes, there is no power of 3 here. There is a power 3 raised to the power of 1 here. And there is no power of 3 here. So 3 raised to the power of 1 is the highest power. So we multiply it by 3. So that's how we arrive at the LCM. All right. Now let's come to this question. Let's come to this question now. LCM is 2 cube into 3 raised to the power of 1 into 7 raised to the power of 1, which means if we look at these two integers, if we look at these two-digit numbers, clearly the highest power of 2 across these two integers has to be 2 cube. Similarly, the highest power of 3 across these two integers has to be 3 raised to the power of 1. And the highest power of 7 across these two integers has to be 7 raised to the power of 1. Only in that case would the LCM of these two integers would turn out to be 2 raised to the power of 3 into 3 raised to the power of 1 into 7 raised to the power of 1, which is 168, right? Okay. Now notice we out of this 2 raised to the power 3 into 3 raised to, into 3 raised to the power 1 into 7 raised to the power of 1, we already have 2 into 3, right? So we already have 2 into 3. So what are we left with now? What we are left with is 2 square. We are left with 2 square into 7. Agreed? Because in that case, notice 2 raised to the power of 1, 2 square, that gives us 2 raised to the power 3 into 3 into 7. So we've already accounted for 2 into 3. Now the question is, how do we reconcile or fit 2 square into 7 between these two numbers? Now, this is where various combinations are possible. Various combinations are possible, and let's discuss this. As far as 2 square goes, let's try putting 2 square over here. If we put 2 square over here, how about 7? Can we put 7 here as well? No. The reason we cannot put 7 over here is because then this number will become uh, 2 square, rather 2 into 3 into 2 square into 7. So how much is that? 2 square is 4 and 24 into 7, which is 168, obviously, right? So this would become 168 and this will become 6. However, what we were looking for was a pair of two-digit numbers. So clearly this is not a two-digit number. In fact, this is a three-digit number. So that constraint that we had to find out a pair of two-digit numbers is violated. In other words, if we put, remember we were reconciling where to put in 2 square into 7. So out of 2 square into 7, if we put 2 square over here, then we need to put 7 over here. So this makes this number as how much? 2 into 3 into 2 square, which is 48, sorry, 24. And makes this number as 42. So now notice we do have a pair of two-digit numbers, right? Again, let's do a basic sanity check. D1 is equal to how much? 2 cube into 3, which basically is 24. D2 is how much? 2 into 3 into 7, which is 42. So going by what we just discussed in the last few slides, what would be the LCM of D1 and D2? How do we find out LCM? We take the highest powers of various prime factors. So what are the highest powers here? For example, 2, among these two numbers, 2 has a highest power of 3. So we put 2 cube over here. Now let's come to 3. This is 3 raised to the power of 1. This is also 3 raised to the power of 1. So we multiply it by 3. And then finally we come to 7. This is obviously 7 raised to the power of 0. This is 7 raised to the power of 1. So the highest power is 7. So we multiply by 7, which would give us 168. And finally, let's also make sure that the HCF is correct. HCF of D1 and D2. And how do we find out HCF? If you remember, the way to find out HCF through prime factorization is you find out the lowest powers of prime factors that are common to both these numbers. Now notice 2 is a prime factor that is common to both of these, but what is the lowest power? This is 2 cube, this is 2 raised to the power of 1. So 2 raised to the power of 1 is the lowest. Similarly, another common prime factor is 3. This is 3 raised to the power of 1. This is also 3 raised to the power of 1. So we put 3 raised to the power of 1 here. And finally, how about 7? There is 7 raised to the power of 0. There is no 7 here. So, sorry, this is 7 raised to the power of 1. There is no 7 here. And hence, you would not consider 7. So 2 into 3, which is 6. In other words, 24 and 42 are or represent a pair of two-digit numbers whose HCF is 6 and LCM is 168. So the answer is 24 and 42 represent those two-digit numbers. This brings us to the end of this session. Thanks.